All right. So, welcome everyone. Welcome, Manmeet, to this session. So, just a bit more context. This is a series of talks which we are hosting as part of the Conference for AI Scientists, which we are hosting or conducting this year. So, this is a collaboration between Loss Fund, which is an independent intelligence research lab in Bangalore, and BITS Pilani. Uh, so, uh, this is, I think, the third or fourth session we are having. And in this talk, we have Professor Manmeet Singh from Western Kentucky University in the US. Currently, we're fortunate that he's in India, so he's able to give us a live session based on the Indian time zone, Steve. And so Manmeet is has also been part of the Indian research ecosystem previously. I think he has worked at uh, Indian Institute of Tropical Meteorology in the Pune in the past. And then most recently, as I said, he's already an assistant professor at Western Kentucky University and already also affiliated with the University of Texas at the Austin in the US. His research interests are in broadly AI for Earth sciences. That is what he's going to cover. And more specifically, I think he's been looking at generative AI, diffusion models, flow matching, disaster forecasting, climate modeling, and so on. So over to you, Manmeet. I think feel free to introduce yourself in a bit more detail, and then we can get started.
Sure. Yeah, sure. Thank you so much, Dhruv. Yeah, Professor Kumar and Dhruv. Yeah. So it's great to talk about AI for Earth Sciences at this venue, and yeah, I'm a climate scientist from by training. I was doing physics-based climate models. I'll be talking about and I then moved on to AI for weather and climate. And then there are downstream applications in disaster, energy, defense, agriculture, space. So a lot of new things that are going on. Uh, I'll, I'll 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 keep talking about my work as well as things which have just started, which are have started to take shape. Whether finance is becoming a thing, SpaceX and those reusable rockets. Recently, China had a reusable rocket which successfully they have been able to intercept. So how space weather itself is becoming a thing now. So forecasts from that perspective. So I would so shall I start, Professor Kumar? Share my screen and
Yes, yes, yeah. Please go ahead. Yeah.
okay, yeah, thanks. So let me write this.
Also, feel free for the audience. Feel free to keep typing your questions in the chat, and we'll take all of those questions at the end of the talk.
Yeah. Yeah. So this is about studying Earth with AI. And when we are talking about Earth with AI, so there are two broad bifurcations that for example are a part of this. So one is the weather and climate world, and then we have the Earth observation world, uh, or remote sensing, which deals with a lot of satellites. There is a booming commercial satellite industry in different parts of the world, specifically in the US, in India. And so I'll be talking about how AI is reshaping Earth sciences. In fact, I would say that the entire there have been a lot of deadlocks, problems in the field that have been are being resolved by AI. So I would start with the AI weather revolution. Now, we often keep hearing about the AI revolution, uh, which basically started with deep learning and convolution neural networks for image classification, and then the regression and the things that have started happening from late 2010s and the past decade. So 2019 is when we actually had this particular paper from University of Washington called DLWP, so Deep Learning for Weather Prediction. Uh, I would maybe briefly talk about how physics-based models actually work. So you have the Earth, so the Earth, and then we have the atmosphere. Atmosphere is a fluid, and so air is fluid. and all the principles that would work on any fluid, for example, principles of fluid mechanics, would directly apply to the atmospheric science. It's a very interdisciplinary field. So the traditional physics-based models, what they have done is that you would consider Earth to be a sphere, and then you would then represent the three-dimensional state space of the atmosphere uh, by either for example, spectral methods, or what we call as the finite volume methods. The exactly how the fluid mechanics or the fluid dynamics community works. But in this case, on a specific three-dimensional spherical mesh, and then you would solve those partial differential equations, which are basically called Navier-Stokes equations in fluid mechanics, but then we call them as shallow water equations in atmospheric science. And you take initial conditions, boundary conditions, try to represent the different processes in the Earth system uh, by whatever best understanding, physics-based understanding that we have, and forward integrate in time. Now, this has been the numerical weather prediction. There was a 2015 paper by so the leader right now in the field is European Center for Medium Range Weather Forecasting, and they if you go and search for the quiet revolution of numerical weather prediction, that came out in Nature in 2015, and they talk about how industrial revolution, which started in 1850s, and then we had the computers and the internet revolution, and then numerical weather prediction also has been a revolution since we had supercomputers and we started solving these large partial differential equations on the spherical mesh. We actually we had a lot of improvements from the methods that were there before that. But the performance of these physics based systems, uh, it the like it was getting really hard to push the limit of predictability or the skill of those forecasting models. And the reason primarily I believe for that was that these models started becoming really big, thousands of lines of Fortran codes, and you would run them on thousands of CPUs. And this work, 2019 deep learning weather prediction model, what they basically do is they consider Earth, the entire Earth to be as an image. So you have the entire lat long map as an image, and then take time t as input, take time t plus delta t. Now you can play around with that delta t. It can be 1 hour, 6 hours, 1 day, depending upon the kind of model you are making. It's a fully data driven model, and then what they did was they used a UNet to map from time t to t plus delta t, and then the convolutions in the unit would take care of the spatial relationships. Now, this particular model was able to reach the skill of the state of the art physics based system, which would have taken like a lot of money to build for 4 decades by different countries, different modeling centers in the world. So that after that, what they did was they published a follow-up paper in 2020 where they considered Earth to be like a cube sphere. So you have four faces along the tropics, two along the poles, and now you consider each face to be like an image, and they were able to surpass the skill of the state-of-the-art physics-based model. Now this was really remarkable, and that led to the interest of the entire big tech ecosystem, wherein NVIDIA built this model called ForecastNet in 2022. Right now, they have the ForecastNet version 3. The principles of ForecastNet are similar to what the physics-based models were using. So we have in two-dimensional space, whereas you would be having fast Fourier transforms, or on a three-dimensional spherical mesh, you would have spherical harmonics, and then you take your lat long data to, so you basically have to respect the spherical geometry of Earth, and then you take it into spherical harmonic space and train it in an autoregressive manner. Now, when you when you have trained it in this manner that you can go from time t to t plus delta t, you can put that back at inference, you can put that back to the model and get t plus 2 delta t. So you can actually roll out a forecast in a similar way in which the physics-based models work. There are a couple of Chinese models out there as well. So Huawei has this Pangu weather. Fushi is a Chinese academic model. Alibaba has its own model. It's called Swin RDM, and then Google built this model called GraphCast, which in which they represented the spherical Earth as a graph. Now that graph is an icosahedral mesh, which exactly at m equal to 6 order it looks like a sphere. So GraphCast really pushed the skill of precipitation forecast, and that's something that we, for example, in India, care a lot about. Uh, Precipitation has been something which drives which is the core for monsoons and drives like agriculture productivity, which is still a large contributor to the GDP of the country. Recently, NVIDIA has come up with this work called Atlas, wherein they are showing that if you have the right representation of the sphericity of Earth in the loss function, you actually don't need to even go to a different embedding space, and they have outperformed everything that exists before them. So it is a like I try to compress how AI weather revolution started, and it has come to the stage that now we have AI based operational forecasts coming out, and there are applications in a lot of industries like energy, agriculture, finance, defense, space, and weather forecasts in general for public consumption. Now, I started working on these things 2017 2018, trying to use deep learning for weather, like improving the weather forecasts. And I would say that to begin with, sometime around 2019 2020, the community was, I think, not that receptive to using fully data driven models. So I built this work on hybrid physics AI models for precipitation and temperature forecasts, and was so we improved like 10x to 20x on out of sample distribution test cases. Like for example, Mumbai 2005 received very heavy precipitation, one of the worst events. We were able to get the right forecast for that, like the right patterns for precipitation at up to 3 days lead time. So that was a thing. And then the second aspect I would say is these Earth observation models. So Earth observation foundation models have like in the last 2 to 3 years has become a really big thing. Recently in India, there is I've been following work of companies like SatSure, which are building these geo foundation models dedicated to India. Really great initiatives that are happening, but at a uh, like NASA has built this model called Prithvi. The goal is basically from satellite imagery, can you get the real time insights for things that matter? For example, burn scar estimation, uh, or the smoke that is happening because of wildfires. Uh, so this Earth Observation Foundation model, they deal with flood detection problems or wildfire detection or those kind of things that involve very high resolution satellite data sets. And Google has these embeddings which are called alpha Earth embeddings. It's a large scale geospatial embedding, and then there are other foundation models from European Space Agency. We have the Clay Foundation model. Now these Earth observation foundation models have applications in all sorts of spaces. I'll be talking about, like in India, for example, we have the Pradhan Mantri Fasal Bima Yojana. So which stipulates that, for example, a farmer, if they have an insurance policy and their crop fails, so there should be a mechanism for verification. Now, how that verification would happen is you need to have plot level uh, satellite information. So that those are the kind of things which are happening, which is what the foundation model is built for, training over multitude of problems, a large model which can then generalize for problems that it has not even seen. And then like the disaster is a central theme in a lot of things that are going on in the AI for Earth these days. So floods, landslides, extreme heat. Recently, a lot of deaths actually happened in Europe because of extreme heat. Road icing and hail are also big problems. Maybe not in tropics, but then in mid latitudes in US, Europe, hail is a big problem. So for even for critical infrastructure, prediction of hail, it damages a lot of things. For example, like your solar farms, you're setting up these solar energy farms, and then it gets destroyed by hail. That's a really big problem. NASA and ISRO recently have launched this mission called NISAR mission. So synthetic aperture radar is also something which is very important. So these are think of them as like radars which are onboard satellites. European Space Agency has like, even that mission is still going on. It's called Sentinel-1 synthetic aperture radar. It's an all-weather radar. So there are two types of satellite missions going on right now. One would be, we would say, as optical satellites, which can not see through clouds. Those are like your cameras on your phone. Uh, and then we have the synthetic aperture radars, which can see through clouds. Now, for problems like flooding would happen most of the times when it rains, and when it rains, you would have clouds. So you getting access to that data is really hard. So Sentinel-1 has unlocked a lot of that ground truth data. And NISAR mission also is in that same direction. So there are a lot of things that we can do with synthetic aperture radar. Particularly important is INSAR. We recently published a paper in ICLR for INSAR, building an INSAR emulator. INSAR is interferometric SAR. So if you have two passes of the synthetic aperture radar over the same point, you can actually estimate the vertical and the horizontal displacement. Now that's very useful for a lot of applications. So think of like you can monitor roads. There are potholes, big potholes on roads or cracks, and then somebody has to report that to NHAI, that you go there on this location and do the patchwork or the repair work. So that can be scaled up and automated to a large scale. You can monitor your buildings, your dams. So this particular case of Palm Jumeirah in UAE, if you search for Palm Jumeirah sinking on Google, it shows, I think, about 5 millimeter per year. That number has come from INSAR analysis of Sentinel-1 synthetic aperture radar for the last 10 years. So very important for critical infrastructure monitoring. And then we have other disasters like and solutions also, like there is universal thermal comfort index, or wet bulb global temperature at very high resolution from one street to another, which is so we have started seeing like predictive forecasts of those kind of metrics. And very important for heat mitigation, as well as for also for energy applications. Like we need to forecast the supply, how much your solar is generating, but then also demand. If you have accurate representation of heat data within the cities, we can actually use building energy models to estimate to develop good demand forecasting for energy applications. And then, yeah, coming to the energy systems. So nowcasting for grids is something that is getting more and more important. Think of yourself as someone who has set up a solar farm. Now the grid is, we have a national grid in India. There is national grid in other parts of the world as well. So you cannot store a lot of electricity. You have to match the demand and supply. But then the solar, it depends upon the clouds, how much solar energy gets generated. So you have to report to the national grid how much your solar plant generate. And then if it under generates or over generates, that causes problems for the national grid. It causes stress on that. This is an example from, you can see from Texas. So ERCOT is the grid in Texas. The yellow one is the solar contribution, solar, and then we have the blue is the wind. The others are coming from fossil fuels. So it's become a very large percentage of the net energy contribution that is coming from these renewables. And then, like, having good forecast of clouds even at a day ahead time scale is challenging right now. So we have started seeing like AI solutions to do those good cloud forecasting. And then we have another frontier, which is S2S. So S2S is like the sub-seasonal to seasonal forecast. Can you predict 6 weeks ahead of time whether there's going to be a heat wave or a cold wave or a hurricane? Now that unlocks a lot of value in terms of how you plan. And also energy traders are using this information, like real traders, and also people who are just there for like arbitrage. So those are things that are going on in the energy space. Then we have like ag. I was talking about the plot level satellite intelligence, and foundation models uh, are giving a lot of value in unlocking that potential. We are also seeing a lot of integration of these Earth observation foundation models and LLMs. So that is also something that is getting very important. Then I was talking about the defense and space sector as well. So uh, recently, I think China has shown that they also have shown a reusable rocket that it would come back to Earth, and they could intercept that. So when those kind of, and SpaceX is the entire thing gets started from that they could reuse the rockets, and the economics of the game, like the entire industry, then starts changing with that. But then when you have to launch those systems, or when those are making re-entry back into space, so the weather that we talk, in terms of like, we as humans live on surface, we care about surface weather, but then space weather is a completely different ball game. So having good forecasts in that space. And then there are, for example, things that are developing now, drone based deliveries. So if you, or autonomous vehicles which would go out in the real world and interact with nature, so they have to deal with those problems, like for example turbulence in a three-dimensional space. Can you predict that? So a drone which is trying to go and make delivery, and for example, if there is a high wind gust at at the level at which the drone is operating, now that becomes challenging for those operations as well. And then think about scaling up the problem. So we need that very high precise weather in three-dimensional space, and space weather information, and all sorts of applications of Earth observation foundation models for defense, surveillance, or change detection. I was talking about using INSAR for displacement mapping. Yeah. So these are, yeah. So space weather and defense are having are seeing an increasing applications of AI weather. It's all coming together, and I think the world of physical AI and world models is kind of converging in some way. That 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 community and this community, they need each other. Uh, Another thing that is very important is water. So whether it is forecasting of floods, or soil moisture, which is so important for agriculture. For flooding, also soil moisture is very important. If you have precipitation and then if the soil is dry, the dry soil would actually absorb most of what you had as rainfall. But then if your soil is fully saturated, then whatever, like it's like you're pouring in water into a glass that is full, it would all be runoff, it would all flow on the surface, and that's your flood. So that's very important with the recent extreme events that are happening. And then everything is then basically coming together into this realm of physical AI. And then we have these foundation models uh, in weather and climate, in Earth observation. There are different groups which are focusing on global applications, regional applications, in all these different spaces. But then uh, trying to solve like real world problems from these foundation models. And yeah, that's my last slide, wherein we are going towards a world which would be a digital twin of the real Earth, as in a digital replica of what would happen in the actual physical space, uh, and at resolutions in space and time that matter for us. Physics is really important for that. So we need to have physics integrated into the systems. And like all of us are living in the physical world, so this has to be accessible. And uh, like it has to be, everybody is involved in this. Yeah. So thank you. That I would end with that. I think I'm at 30 minutes in this, and I'm happy to take any questions. uh, yeah.
Thank you, Manmeet. I think that's very interesting. So let's open the floor for questions. There's one definitely. So there's one question from Sakshi. She's asking about the uncertainty. How do we compute or quantify the uncertainty associated with these foundation models, with these AI models?
uh, yeah, so that's a very important question, I would say. Uncertainty quantification, I think we have the entire field of weather forecasting. uh, if you see the traditional weather forecasts, uh, I would, okay, let me go to 1950s and 1960s. The development of computer science or computers, those large computers which were of the size of an entire room. The first problem, so weather forecasting was the one that was pushing the development of those large computers. And there was this person whose name is Edward Lawrence. He was running these three there are these three partial differential equations, which are called Lorentz equations. And very simple set of equations which have the solution of those equations is, it's in three-dimensional space. So it comes as a butterfly, which basically oscillates around a common, which they call it as an attractor. And that gave the birth to the theory of chaos and nonlinear dynamics. And when Lorenz was running one of his experiments, like those were simple equations, he was solving them. uh, I think something happened, like that computer went off or power went off. And you can, let's say, he was running those simulations, which in the RAM, let's say they were having a decimal limit of 32 decimals, but then your disk storage can save only up to 16 decimals. So you would basically lose that. But those are like 16 decimals after the 16th decimal. So what I did was like stored those initial conditions, but reran those simulations from there, and then reached out to some output. And then he ran the simulation again from the same initial conditions, and both the outputs were completely different. And that has been the foundation of the entire field of weather forecasting, wherein ensembles are running different, so perturbing initial conditions, and then uncertainty quantification has been the core So if you look at operational weather forecasts that are issued by India Meteorological Department, those are not coming from like one realization. Those are like ensemble forecasts. And then there are methods to ensure that you have like uncertainty quantification is taken care of. We have something called as the spread skill ratio. So you have the different members, and then what the spread is between the members relative to skill, which can be, for example, root mean squared error. So that should be something like it should be around 1. So from point 8 to 1.2 is something that we consider. If we have, then it's a well dispersed forecast. Now those ideas in the traditional numerical weather prediction world, when we are coming to AI weather forecasting, diffusion models and flow matching models, they are unlocking the same kind of uncertainty quantification. So yeah, I'm sorry for going too back 1960s, but then uh, uncertainty has been something which is at the core of the entire field. Yeah.
There's one more question from Igne Patterson. For different physics domains driven by PDEs, there will be overlapping AI code patterns. Are there libraries implementing these basic AI patterns and thus simplify implementing domain specific code using these basic patterns? So I think what he's asking is, are there any libraries which are kind of, providing these out of the box AI support, implementing some of these differential equations, implementing these
Yeah.
different physical models, etc.
Yeah. So yeah, there are some libraries. I would actually paste one of those links in the chat. So this is called Physics Nemo. So Physics Nemo is a library which is from NVIDIA. They are not just in weather but also in aerospace and different other domains. You can run neural operators on PDEs. You can go there. They have tried to make sure that the source codes of and they Physics Nemo deals with all sorts of stuff like molecular dynamics or structural mechanics, reservoir simulation, healthcare, geophysics, computational fluid dynamics, and they have tried to reproduce if a paper is maybe not from NVIDIA. So that is a really good one that I think that should be followed. There are others as well, but which are like specific to domain, but a very generic one would be, I would say, Physics Nemo. Yeah.
All right. There's some question on, can we get any information on how much accuracy has improved in the prediction using AI and without AI? Maybe that's what Hemant is trying to ask. And are there any gaps between the physics based approach and the other approaches?
Okay, so there is a lot of improvement that has come in from using AI based models. To give a perspective, uh, we have been trying to push the skill of precipitation and temperature is relatively easier. Precipitation and soil moisture are very hard. Uh, in India, we have been trying to push that skill from a long time. I would say maybe last decade. If you see any research on going on in monsoon, anybody doing anything in the field, let's say I'm someone from instrumentation, I'm saying I'll set up a radar. That radar will give me will get additional information, or I am someone who is setting up a station observation, or I want to send a new satellite which measures something. The whole premise of those arguments was those papers say we will do A, B, C, and then we will improve precipitation forecasts, and that would help the farmers. We were a predominantly agriculture economy. That things have changed in the past 2 decades, but really, how much those forecasts improved? It has been like it. We have had like really good missions going on, but what, for example, these AI weather models have done. Uh, just to give a context, so European Center for Medium Range Weather Forecasts, they incorporated so they had a physics-based system called IFS, Integrated Forecast System, and now they have something called as AIFS, so AI forecasting system, which is operational, and it has been shown across regions, across different space and time regimes, that AI weather models have pushed like substantially pushed the limits of physics-based models, while being completely different in approach how the physics-based models are built. Yeah.
Uh, Dr. Singh, just to continue that, right? Like, uh, what would be an intuition to build around what are the limits of these physics-based models, right? Like, I think this was another question in the chat, which is it that we haven't been able to figure out the complete physics of everything that goes behind this
Yeah.
prediction, or is it just the scale of the data that's absent? So, what is the limitation which is allowing AI to unlock the scale?
So I would say, yeah, I think in your you mentioned a point in your question, I think, which is the answer to that. Uh, think about systems like clouds. So at for example, we are in July 2026. This is the best time in the history that we are observing the three-dimensional structure of our atmosphere and earth system. But in the past, when we did not have satellites, we could only measure the phenomena that is happening on the surface and indirectly infer from things that were happening above. We could never go and put a sensor in the clouds. Our understanding of clouds has been very limited. Like, if you think of what we are taught, for example, in high school, you have water evaporates, becomes water vapor, goes up, forms clouds, comes down. What exactly happens at what elevation, at what temperature, relative humidity, how does water vapor transform to liquid droplets? There are processes within clouds that happen. For example, entrainment. So entrainment is how a cloud grows and it takes in the water vapor from adjacent areas. Now those things were like our best understanding, approximated in terms of statistical equations in the physics-based models. And also, for example, we are living in tropics. These were some experiments that took place, for example, in US, wherein they would have had a weather balloon, and they built a statistical relationship with the precipitation there. And 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 also, our problem is hard because we are in tropics. The energy, solar energy that we receive, the entire energy itself is higher. So predicting, it's more non-linear than the world, in the US and Europe. So people often say that the forecasts in the mid latitudes are better, but they are much worse when you are in India, let's say. One, the problem is hard. Second, our understanding, and then our understanding that has been encoded from a different part of the world into a simplistic statistical equation. In that model, we have been using that for our region. And what these AI based models are doing is they are just brute forcing on the data. And there are a lot of physical processes that we maybe don't understand. Like, nobody has even thought about it, which are going on. And the deep learning model has unlocked those physical processes. And maybe that's the reason we are yet to go into the explainability part of why AI weather models are so good. There are some works on that, but then uh, yeah, I think we might see some progress on that, but that is also something that is yet to come. But definitely a lot of progress in the AI weather models. Yeah.
Sounds good, Manu. Dhruv is asking a follow-up question. How much of the problems in AI for Earth sciences are intelligence problems versus hardware and more accurate sensing issues?
Uh, so so the question is that how much of the problems are intelligence versus hardware? If I understand this correctly, so by hardware you mean that we have uh, we have we don't have
More
a
sensors, for
observation.
example. Yeah.
Uh,
If we had more ways to collect data,
mm,
could we actually solve the AI for Earth sciences problem more accurately, given that now we have
Definitely,
so much
yeah.
advancement in
So
AI?
so definitely yes. But if you think about it, like the original 2019 deep learning weather prediction paper, uh, if someone would have proposed that in 2016, 2017 to a senior climate scientist, it would have been considered a stupid idea. So it's about the sensors, definitely yes, about the data, but it is also about the architecture and the model. So with the existing observations, there is still a lot of stuff that we can do with the advancements that have been taking place. For example, in the diffusion world, in the flow matching world, in stochastic interpolants, you can just do a lot of stuff in those realms. Yeah.
Also, can we also use these foundation models to get insights about physics and chemistry, or are they mostly for applied forecasting and research?
Uh, I think, yeah, definitely we can do for understanding physics and chemistry. There, I've seen some papers where they have tried to use deep learning to get the underlying PDEs, the partial differential equations. Uh, so that has been one area that has been underexplored in the physical AI world or sciences. The other side of the story is, so there is an interest in atmospheric there is an entire field of atmospheric chemistry as well. We have a big problem of air pollution, for example, in Delhi. Good forecast would be very useful. There are limited model, like I think there is only one model which gives. So Microsoft has a model called Aurora, which gives forecast at 40 kilometers, and it also has air quality parameters like particulate matter less than 2.5 micron, which is very, like, it goes in, it doesn't come out. It's so dangerous for your health. But it's at a 40 kilometer by 40 kilometer grid. You would get like one number. Entire city is approximately that size. We need to go into high resolution. But on the other side of the spectrum as well, uh, like if you think about it, this is a chemistry application, right? But atmospheric chemistry application. You can understand physics and chemistry by discovering the underlying partial differential equations, and also doing a lot of stuff that's going on, for example, AI scientists world. uh, yeah, and then going into the application side as well. Yeah.
So another interesting question from Dhruv, and this comes from this recent hype around auto research, AI autonomously doing research using these coding agents or AI agents in general. So
Yeah.
how good are these AI agents? Not for products. Have you tried them? And how good they are in building these uh, foundation of ML models, fine tuning models, building fine tune models for these earth sciences applications, and how much human expertise is still required at the moment?
I would say, yeah, they have made, for example, they have made me really productive. I use Cloud Code all the time these days. They but but also that it has, I think uh, the kind of inputs that, for example, I give, and then uh, the critical aspect on the feedback that I can still give to these AI agents does the job. And if someone who would not be having uh, like detailed insights uh, into the domain, for example, it like running them autonomous in a, I think loop engineering is becoming very popular these days, right? So maybe we still have time that we can start solving them as in a completely autonomous manner. uh, yeah, that's what I think right now. I would love that to happen. It would be next level of productivity, and we can solve so many of these problems which actually matter for the this like social good in general, right? Yeah.
I think there are a couple bunch of fruitful questions around like how do we get started? Is it necessary to do a PhD in this field to do a significant impactful work in this? Are there any industry rules? So, I mean, how do we get started if I'm a new guy? Is it necessary to do a PhD? What kind of roles, career aspects are there, career options are there if we pursue this?
Yeah, so I think to start, there is, I mean, with these AI agents, there is no barrier these days to start with I think anything, uh, and that would be. I mean, I think it's even more easier to start in our sciences, and if you want to start, I would say try exploring the NVIDIA's Earth 2 ecosystem. So they have Earth 2 Studio, they have Physics Nemo. So Earth 2 Studio, you can run different AI weather models. Even they have been incorporating flood forecasting systems. Google is doing a lot of work, and then you can follow ECMWF's work. So they have a library called Anemoi. Anemoi is like the counterpart of Physics Nemo, but from ECMWF. And then there is something called as Credit. So Credit is from NCAR. NCAR is National Center for Atmospheric Research in US. It is also similar to Physics Nemo. So these are like open source libraries. People can, and they are very receptive to people doing open source contributions. Reproduce papers, for example, for which uh, your own implementation of code in these open source libraries that would help others. That is something which is very useful. But also, I have seen the transition of this entire field from being a purely academic field into very commercial field. So the main conference, like the main event that we have annually, like there would be two, I would say. For example, one is American Geophysical Union's annual conference, and then there is American Meteorological Society's annual conference. We also have the European Geophysical Union's annual conference. So I would say, let's say maybe three big events. If you go there or you attend virtually, you would see that it's getting mostly occupied by industry folks, companies that are doing insurance. That are, if you are, for example, in Florida, companies would not give you home insurance if your house is in a location which is having high risk of hurricanes. Uh, Energy companies, energy trading companies, uh, these space defense companies, satellite companies. It's a huge growing ecosystem, which I think it's becoming entirely commercialized right now. And I don't think a PhD is required. PhD helps, but that's a very uh, I think people should decide at their personal level whether they would want to do that or not. But I see a lot of people doing great work even without a PhD. Yeah.
Dr. Singh, like if I have to push on that a little bit further, right? Because I think that's what also my question was in Karthik's. So like this is all great. Of course, there's no barrier to get started because of agents now, right? But I think the biggest barrier within entry level folks is like sort of coming up with the right problems, right? So are there specific, let's say, problem statements which are sort of super top of mind for you right now, which are at the frontier right now, where folks with the CS background or ML background could start applying their brains. Like, yeah.
Yeah. So the all these, like I would say maybe these 3 to 4 problems wherein short range. By short range I mean 3 to 5 days lead time, high resolution in space and time. So every hour you have to give the information, and let's say at 1 kilometer by 1 kilometer spatial grid. Uh, that is a big problem, and uh, any solution in that space gives you a lot of value to a lot of industries. That is one. Then going into the S2S, sub-seasonal to seasonal scale, long lead time forecast, but even at coarser spatial resolution is again, that is super important. Then a couple of things that I talk about: energy space. So nowcasting, like day ahead, solar nowcasting. That's big. There are some of the problem statements which are maybe not that people don't consider developing high resolution data sets to be cool, but then those are like, if you end up making those data sets, now there is actually a marketplace for earth science data which is called Earth Mover. uh, I am seeing a growing trend of companies putting in free data. So there is this company called Spire who developed an AI S2S model recently, and a lot of energy companies and uh, different stakeholders who are in agriculture stakeholders who are interested in AI S2S data, and their claim is that their model is the best in the world, better than even ECMWF. I think even in India there are some of the clients who are buying their data. They put in a free version, sample 3 month data on Earth Mover, and the remaining data is paid via the API. So if you can make your own data at high resolution, host a sample data there, uh, put out an archive preprint. If you can fight it out, show that, go present out in the community, show that your data is the best, it can add value at high resolution in space and time, or at long lead time. It can be anything. It can be temperature, it can be precipitation, it can be soil moisture, it can be winds. Now, when we talk about winds for wind farms, that is like winds at 100-meter height from the surface. That's what they're looking out for. All sorts of things like sea level, coastal insurance companies that deal with the coastal areas, they are looking at the high resolution sea level data for future. So that like, yeah, there is a lot, if you think about it. Yeah.
Sounds good. There's one question from Pratiksha. She's asking, uh, what kind of models can be used for problems related to marine pollution, like the Great Pacific Garbage Patch, and so on, if you have any idea.
uh, I think maybe my internet is bad, or maybe
Yeah.
I can you maybe repeat that question?
The question is, what kind of models can we use for solving problems related to marine pollution?
Uh, yeah, for marine pollution, I think maybe the question might be related to the plastics in the ocean. that, I've seen some work in that direction where people have tried to identify uh, polluted zones from satellite data. So that would be something that is important to do. I'm not up to date with where that particular space, what they are doing, but yeah, doing anything with the satellite data that improves the detection or quantification of marine pollution. And there is a lot of interest going on around water quality. So fresh water is a scarce commodity, and it's I think we don't realize that, but that's compared to the global water resources. So any kind of pollution identification, sources of pollution, for example, from satellite data, that would be great. There are people are doing all sorts of work in this direction, collecting data from there, developing models, whether they are physics-based models or AI-based models. Uh, yeah, physics-based model community has done a lot of work in that direction. So I believe you can improve by using developments in AI in that space. Yeah.
And, Aditya, I think you have your hand up. Do you want to do the last question for the session, and then perhaps we can close? It'd be great if it could be a short one. Yeah.
Yeah, yeah, it's a short one. Don't worry about it. So, regarding the model architectures, right? Like I've seen several papers. For example, you have nested transformers, right, where they kind of compute like different parts of the embedding phase and stuff for like different inference scenarios. So, I'm just curious: is there any specific architectural components in the model that you can specifically change for Earth science? Has there been research on it, and is there a upcoming research field on this?
Yeah, so I think that is something that recent. For example, there are two recent models that came out in January, or and January, February, March. Three models, I would say. One is Mosaic, another is Atlas. And then there is also a model from NVIDIA which is called StormScope. What they are doing is they are, I think, trying to combine everything that is best from the previous architecture. So diffusion transformers are working really well. You play around with the ablations in that, and also I think the stochastic interpolants type of models. So architecture is definitely pushing. Still, it's pushing it forward. The getting a better model with the same data. For example, the ERA 5 global uh, 25 kilometer data that we have. So we are still seeing models which are pushing on architecture. If you see the forecastnet version 1 and forecastnet version 2, the version 1 was based on adaptive Fourier neural operators, and version 2 was spherical Fourier neural operators. Now spherical Fourier neural operator would take into like spherical harmonics, something like fast Fourier transforms on a sphere. The major difference, if you see NVIDIA's main blog, is that the AFNO, the first version, it just blows up. It gets like instabilities, and you start getting noise. And then we have improved a lot, but then there is a lot to do. We have not reached a state where we have perfect models, or where we can say that we have achieved digital twins. And architecture is still unlocking that the next leap forward. Yeah.
Is there anything specific about earth science as a topic which translates into architecture, or is it just right now about trying different architectures, seeing what's working? Like,
Yeah, I mean, I would say earth science, just like any other field you pick up, like biology or
yeah,
chemistry. Yeah, I think you try your data on,
right.
yeah, it's just the data, right? So
Mhm.
yeah.
Makes
Nothing specific with any architecture and the
Mhm.
the field itself. Yeah.
Makes sense. Thank you for the great session. Learned a lot. Thank you.
Yeah, thanks.
So I think let's try to wrap it up in maybe one last question from our side. So Manmeet, I think given the latest advancements in AI, like where do you see this AI for earth sciences going in the next few 2 years, 3 years, or maybe 5 years, 10 years?
So I think it's becoming a very commercialized field. As I said, the AMS and AGUs is becoming like IEEE used to be academic at some point, and then it became a very industrial field. So I see it like all sorts of different applications, whether you talk about drone-based delivery or autonomous vehicles, or space weather, wherein you have reusable rockets, and like things that concern day-to-day life, like extreme heat or disasters, energy, agriculture. So everything that like we live on this planet, right? So and it's getting more commercialized, and I think that's really good. Recently, the National Commodities Exchange in India, they launched a future sticker which is called Rain Mumbai. Now, Rain Mumbai is the average of Santa Cruz and Colaba rainfall, and you can actually trade in that. There is active volume going on in that, and that I feel is a really good start, wherein now you have associated a financial incentive into improving the forecasts, and those kind of things are happening at a global scale as well. Like there is, for example, we have Zerodha in India. There is Robinhood in the US. They have these prediction markets for weather. If you can predict the day ahead maximum temperature for LA, it's a very uh, liquid entity. So you can make a lot of money there. Talk about finance, talk about uh, air quality and health. Uh, it's getting more and more commercialized. That's where I see the field going, and people are discovering newer applications. So yeah, I shared the things that I could do. Yeah.
Me? I think with this, I think we're already over time. So let's thank the speaker once. So thank you, Manmeet, for joining us today and taking out science, sharing your experience in this AI for science. I think it was definitely a very insightful session. Thank you again. And of course, I think folks here will reach out to you separately if they want to like to collaborate with you, work with you. That's obviously very interesting. So, yeah, again, thank you, Manmeet, and yeah, to rest of the folks, I think, and for Manmeet also, we have some sessions lined up tomorrow, Saturday, and Sunday as well. Sunday, we are meeting, for example, with Shiv Kumar Tilman from ANRF. So definitely, please do try to join the session. Tomorrow, we are having the, you can say, quote unquote, the first session for the conference, in the sense that the session where we'll talk about overall conference experience we had, AI reviews, AI authors, and so on. So please, I think Dhruv Trehan has already shared the session links in the chat. So please register for these sessions and look forward to seeing you again tomorrow in the event. Thank you.